I have a predecessor, Michael Kenzel was here last week, so I'm gonna have to work hard to do get to that level. He's really good.
How long did it take you to get here from Gainesville?
2 hours and change if there was little traffic.
Okay, welcome everyone for our another episode of the FSI Seminar Series. And today we have Steve Miller, Dr. Steve Miller, Associate Professor of Mechanical and Aerospace Engineering from University of Florida. And he's there since 2016. And he leads the theoretical and fluid dynamics and turbulence group. Prior, he was a aerospace engineer at NASA, Langley Research Center for 7 years. And he received his PhD, then MS in aerospace engineering from Pennsylvania State University and BS in mechanical engineering from Michigan State University. He's a recipient of DARPA Faculty Award and NASA Early Career Achievement Award. And today, he'll be talking about the overview of aeroacoustic sources from rockets for prediction of radiation intensity and coherence.
All right, thank you very much.
Yours, please take it away.
Yeah, thanks a lot for the introduction, and I really appreciate being invited here, and it's a real honor to come to the Orlando area. I've got a lot of friends up at University of Central Florida, and I hope to make some new friends here. And I learned in my short time here that we have a very diverse research group here. So it occurred to me there's probably nobody maybe who studied turbulence or acoustics in the room. So that probably means I'm going to just talk at like a really high level, because I'm going to show you kind of like a problem solution benefit. What are the problems we're facing in this field? What are some of the solutions and outcomes? So I'll try and focus it that way and just really explain things from the high level. I have a lot of slides, and these are from different programs, so I'll try and explain how it all fits together. So I'm going to talk about basically rocket exhaust and noise from rocket exhaust, which is really loud. It's probably likely the second loudest sound that's man-made. What is the first? Of course, it's a detonation of a nuclear weapon. So it's pretty loud, rockets. And this is some of the acknowledgements here. We have Startup, which is a government organization, and some from this organization, and a number of graduate students who've graduated, and at least the ones on this list have moved on. Outline of the talk, just introduce myself just briefly. I think I've been told to shoot for 40 minutes. And we'll talk about the turbulence from high-speed rockets and also aircraft exhaust. It's the same physics from a little compressed air can all the way up to, say, a volcano volcano going on. So it's kind of interesting to have similar fluid dynamic solutions. I'm going to talk about basically 3 different ways to look at the problem and understand it, which is 3 different funded research programs. One is instability theory. So some people in graduate school may have studied like controls and things are unstable. Well, like boundary layers are unstable. Well, it turns out rocket exhaust is unstable, and we try and predict the instability waves. Another way is using supercomputers with large eddy simulation to actually simulate and CFD these flows. And the final one is aeroacoustic theory, and I'm really a theoretical modeling type person, and that's where probably my bread and butter is. And I'll try and explain to you how we make a prediction of coherence and cross spectra in rockets for, say, like Space Launch System. which I used to be involved in. So just on my background, I have a bunch of slides like this. This is my group. Study of turbulence goes back a long time. Many things people worked on it, like Da Vinci. It's idolized in art by the Japanese. That's a $50,000 painting. The print you can see in the Nut in New York. I also like art history, so you might get some history in here. Heisenberg wrote his PhD dissertation on turbulence. It's still referenced today, but after that he quit because he felt he couldn't make progress in the field. And he decided to go start a field called quantum mechanics, which I hear is important, but we're talking about continuum phenomena. And so that's what my group does. We're really an analytical and computational type group. Just more introductions on myself. We teach a number of courses, compressible flow, graduate, undergraduate. That's just like high-speed aerodynamics. Those are required courses usually. Introduction to CFD or computational fluid dynamics. With the math department, we teach a joint special topics just on the Navier-Stokes equations. It's about the history, methodology, analysis of Navier-Stokes. And if you can just prove solutions that exist of the Navier-Stokes equations, then you would win a clay math medal, $1 million and probably a Fields medal. So that's outstanding. And that's incompressible, so it's quite limiting for aerospace and a class in turbulence modeling. So now I have a number of slides just on all the projects I've done just at Florida in the past 6 years. We do thermoacoustic instability modeling with FOIM and the combustion folks. So if you have a rocket engine or a jet engine with an augmenter, it could be unstable and acoustic waves form in there and it blows up like that quickly. And when you see all those beautiful photos, if you think they're beautiful, of all these rocket engine test stands blowing up for the last 70 years, a lot of them have been, especially in the 60s and 70s with the Soviet Union and American allies, due to that instabilities. We do plasma flow actuation for flow control. We have done turbulence measurements in the National Science Foundation Boundary Layer Wind Tunnel, which is at Florida. And you can, if any of you come up, we can give you a tour. Anybody here is invited to come up and I'll give you the tour. We build nozzles and test them in our labs, and that's from my collaborators, but we do the CFD for that. Previously, NOAA funded us to study tornadoes and turbulence from tornadoes, and we went out with Texas Tech to chase them. So some lucky undergrads got paid minimum wage to go to Texas. And these are the pictures of the tornadoes we captured with our instruments. And we compared the deformation of tornado turbulence in the NSF tunnels with CFD data tornado formation. The idea is that you would actually like track the infrasound from a tornado and triangulate it as it's forming as an alternative early warning system. So the US government has deployed infrasound microphones around the United States to detect tornadoes. Why are they already there? And you want to give me one guess?
Why are microphones already there?
Yep, why are the microphones already there? They weren't put out there for tornadoes.
Oh, UFOs.
UFOs is a good guess, but it's actually when countries like North Korea has a nuclear weapon, they sent low frequency waves around the globe, and you can detect that as a unique test. So that's the reason you have microphone infrasound nets. So we can use them to detect tornadoes.
What do these look like? They're just randomly out there and
yeah, they're real small. A microphone's real small, and they're specially designed for infrasound. You can also buy an infrasound microphone from companies, but these are very, specific designs that are let out at UT Austin.
So how often have they detected something?
They're going to detect all kinds of seismic events. So they'll detect, everything, like even underwater earthquakes. Yeah, they can be detected. So that's a whole geoacoustics field. Yeah, that's a great field. Absolutely. Okay. Yeah, good questions. Keep them coming. We do rotorcraft. We do aerodynamics, acoustics of rotorcraft, blade design. We manufacture the blades. You probably read in Aerospace America. There's eVTOL design, and what we do is put plasma actuators to reduce vortex strength or increase aerodynamics and lower noise, and that's supported by DoD, NASA, and some companies. This is all jet work from the US Navy. Jet structure reaction, I was just talking about trying to get involved in that field. We did a little bit of work on the left where you have, say, a plume coming through a nozzle when you're taking off from another planet or any another planet, what happens to the surface. So we do the CFD and acoustics. This is a little spy versus spy graph of how you fly a vehicle. through a room and say, I want to do surveillance on the room, people will hear that vehicle, but they may not be able to perceive it. For example, in this room, there could be a vehicle flying around that you can hear, but you won't notice. And that falls into the field of psychoacoustics, that we can change the acoustics coming from a vehicle so that we shift its frequency so you don't perceive it. So these are the types of things that the DoD and DARPA are thinking about
I
sometimes.
bet.
Kind of cool.
I'm interested in that.
Yeah, maybe back to more civilian applications. My collaborator, Kylie and Ifyu, they're associate chairs of our department. We build in-house and design and fabricate rotors and test them in the lab for aerodynamics. And I do the simulations and predictions. So you see here's some rotor sets that you might see from a new electric vertical takeoff and landing type aircraft, which I hear they're doing a lot of work here at University of Central Florida, just north of us. And so those are just plume type calculations. We do DNS with particle laden turbulence. So there's kind of a few criteria. Basically, you have a cube, use a supercomputer, you simulate the turbulence, you learn something about turbulence, put particles in the turbulence to understand how it changes the turbulence. Why do we do that? Because we want to understand how particulates and solid rocket boosters alter the exhaust. And these are some large eddy simulations of real gas flows on the right.
What size particulates?
They range, I'm talking on the order of 1 to 10 to 100 micrometer. Yeah. So we have test data from Marshall and NASA Ames where they give it to us and say, can you analyze this data?
And these are like unburned from the solid rocket booster, or
They're burning. So a particulate can continue to react through the entire flow here. Yeah, as it goes out. In fact, they're moving supersonically, so they create their own shock waves. And sometimes they go outside the jet plume and create additional noise that's considered like launch pad noise for solid booster. Yeah.
how big are the particles in the solid rocket booster? I didn't even know.
There's a whole range of particles. So what we do is we use a probability density function as like an inlet boundary condition to that booster.
I see. Okay. All right. Thanks.
Yeah, no, that's a good question. I like you. You ask good questions. Yeah.
If you let me, I will.
I wish we had more students in my class who ask questions. Sometimes they get really quiet. I teach at 8:30 in the morning and I don't drink a lot of coffee. But I drink coffee, so I should drink coffee.
Here they're bringing in students for 7:30 exams apparently, so.
Okay.
I have 2 classes this semester. They're at 7:30.
Yeah.
Wow, your classes are at 7:30.
Yeah.
That's amazing. So if you are at University of Florida, we don't start till 8:30 in the morning. So
Until this semester.
I admire University of Central Florida. You work so hard, you start at 7:30.
Yeah.
A whole hour better than University of Florida 8:30. So I commend
No
you.
issue.
So the people really paying my bills right now is DARPA. And the goal of the DARPA program is to predict the aerodynamic near field without CFD. Our goal is to eliminate CFD because CFD is very expensive. And we want to find calculations of airflow of the vehicle. So here's what they call a power law wave rider. Wave riders are being deployed by the People's Republic of China. The Russian Federation are being used in the theater of war in Ukraine. America's a little bit behind in hypersonics, in my personal opinion. So we have a workforce development problem. And so DARPA is funding my research program through an award, DARPA Faculty Award. And so there's some of the predictions. It's a power law wave rider, and you're seeing contours of coefficient of pressure. On the left, you see predictions of the near field. This is the change in pressure with axial distance, a distance away from the wave rider. Why do you want that? Is we want to predict the sonic boom from hypersonic vehicles. And I'll let you imagine the reason why you want to do that.
Predict and eliminate, or?
It's probably impossible practically to eliminate a
Okay.
sonic boom from a supersonic vehicle.
Okay.
There's actually designs by again Adolf Boostman, who is the original chief scientist of Langley, NASA Langley, and he proposed a Boostman biplane. It's actually a supersonic biplane, and it could be theoretically possible to design that to have no boom in supersonic, but nobody's ever done it. So there is a possibility that people have been thinking about, but it's never been done. It can be done in 2 dimensions, but not 3. Okay. Atmospheric turbulence, we characterize atmospheric turbulence and construct it kinematically to study sonic booms. So that's a constructed atmospheric turbulence using MOST theory, which came out of the Soviet Union in the 1950s and 60s. It's still one of the predominant theories. Anyway, that's a big research overview. I'm really here today to talk about some things we've done, which is the noise from rockets, which are jets. And I'm not really talking about structural response because that's really someone for a structural dynamicist to do. So in the wind tunnels, when you're designing, say, a space launch system, which is flying, about 10 years ago, I was involved in the committees that took the wind tunnel data and analyzed it and asked the tough questions. And what they want to do is take different coup lights on the model, and that gives you like high frequency measurements of unsteady pressure. And you take those 2 points and you find the cross correlation in cross spectra. The cross spectra, which is like a power spectral density between 2 points, gives you the structural response. So the whole point of the program is to find the structural, like the cross spectra, the unsteady pressure on the rocket. Not at one point, but every point in its relation statistically is a function of frequency. And that's given to the structural dynamicists to see if the rocket and re-radiation of acoustics inside is going to make your payload break apart or your rocket nozzle break apart or something. So that's a very difficult thing. Let's just look at some general slides here. This is rocket launches. They're ever increasing, which is good for us in the aeronautics and astronautics industry. And just recently, I think because of commercial space back in here, it's starting to grow rather quickly. And everybody seems to be a little bit jealous in the United States of our commercial success. 10 years ago in NASA, most NASA people, including me, said commercial space is stupid. It's not going to work. We have to have government do it. And a lot of previous astronauts turned up their nose at commercial space too, like Neil Armstrong. And so all these years later, I'm eating humble pie, and I had to send an email to one of the first, I think it was number 12 in SpaceX. He's still there. And he wanted to hire me as a grad student in SpaceX. And I said, no, I want to go to NASA. And anyway, it's a funny story. So you always have to be a little humble. Question.
Do you know what partial failure means in this plot?
Oh, no, this isn't my plot. My view is probably failure means destruction, success means made to orbit, and partial failure probably means screw up, in my opinion. Or made to orbit. Like a partial failure, in my view, would be the satellite made it to orbit, but it doesn't work. And one reason satellites make it to orbit and don't work is because of vibrations on the truck to the launch pad or vibrations during launch, which is driven by this type of program. Yeah.
That's what happened to our set.
But we have a few slides here. I think I got about 30 some minutes to, so hopefully you have some coffee. This is on the right. This is actually a scale model of the cancel program. I think that was from Ares, which is a NASA program. I was involved in that on the outside. On the left are jet takeoff. So let's say you're an 18-year-old person and you decide to join the United States Navy to serve your country. And they put you out on the flight deck. And the first thing they do is they give you a custom earplug. They give you active control over the headphones. And you stand about 20 to 30 feet away from aircraft. And you will have permanent hearing damage in 12 minutes. That will last the rest of your life. So you are all paying taxes to the VA, which gives over $1 billion of hearing loss a year, just in benefits. So there's a huge motivation by the US government to reduce noise from aircraft in this situation. In the lower left is a Boeing Dreamliner demonstrator, and really put like these like chevrons on the nozzle to reduce noise. Rocket launch, when you design an engine, you basically do almost nothing to reduce noise because it hurts performance. How do you reduce noise? What's the first rule in rockets and jets? You slow down. It's kind of a joke, but it's real. The first thing you do if you're a fighter pilot is turn off your afterburner or augment. Here's some more launch pictures. Another part of the problem is vibrations on the rocket surface itself. From the turbulent boundary layer and separation and shockwave boundary layer action. These are all things that drive heat transfer and create vibrations during ascent. Because even if you make it up there, like I mentioned, your satellite may not work. NASA Ames does these rocket studies where they invert a small rocket engine and they take test data. And up here on the right, they actually have a microphone array where they're measuring the acoustics in the near field. And the idea is that if we can measure the acoustics and have this large database, maybe we can analyze it and understand the physics of turbulence and reacting flow. It's a huge problem. And we're in the business of prediction. So our goal is to predict that flow field. At the end of the day, we want to use a supercomputer. We want to use a simple equation to tell me what the statistics of the pressure are near the jet and at different places around the launch pad if you're doing rockets. And it's a huge challenge that has been worked on for 70 years by some of the best mathematicians. It's been called a curious problem in fluid dynamics by Sir James Lighthill. He's the Lucasian chair of math at Cambridge. That chair was held also by, anybody know the history of Lucasian chairs? Sir Isaac Newton. Okay. Who invented string theory? George Bidell Airy. Stephen Hawking. You could keep going. Anyway, it's a very prestigious place. So let's just talk about the physics. So here's a novel, and the flow is going left to right. And this is your supersonic jet exhaust. A jet is a rocket engine, is a jet engine. And in there you have a shock cell structure. Those are those beautiful shock diamonds you see when they take off. And outside this plume is all these funny looking waves. And we classify them in different ways. People even argue about them, and they're from different types of turbulence. So some might be from the large scale structures of turbulence. They're the large eddies that contain most of the energy. Some are from some small, tiny little turbulence called the Kolmogorov scale, named after Andrei Kolmogorov. He's probably the best mathematician who came out of Russia ever. They're named after him. And then there's other noise that's from the shock waves interacting with the turbulence. That's called shock wave turbulence interaction noise. And that can create strong tones that go up to 180 dB, which is deafening. And it's so loud that it can break apart nozzles. One great example is the original F-18 aircraft. Its tones from the jet flow were so loud that the nozzles were disintegrating in 100 flight hours. The F-22 has a similar issue, which is still ongoing. So this noise is loud, and what you see are what we call spectra. So the x-axis is non-dimensional frequency, and the y-axis is sound pressure level in dB. So these are measurements, and this might be the downstream direction. Your spectra looks like this and has a peak frequency, and this is a laboratory scale nozzle of 140 dB. A chainsaw is about 120 by your ear. So if I was not in a friendly mood, I would hold up a chainsaw, rear it up to 100% and hold it maybe this, a meter away from your ear. And that's really loud. And over time, you'll get hearing damage. So this is a log scale. So it's another 20 dB higher. How much is 3 dB? Let's say I have an F-18 aircraft and I turn off one engine. Your dB reduction will be 3. So every time you add a rocket engine, you only go up by 3 dB. So that gives you an idea of how many dB 20 dB is. It's a lot. That's a lot of power. So the goal is to predict this and understand it. And once you do, you might be able to devise some way to reduce the noise, which is hard. This is a single plot to show you the effect, and these are predictions. X-axis is serial number, y-axis is sound pressure level in dB, or excuse me, non-dimensional frequency, but is in dB. And it's a Mach 1.5 jet, meaning the jet flow coming out of that nozzle is 1.5 times the speed of sound. And you see 3 figures from the predictions. These have been validated against the Ames experiments for solid rockets. The black line is solid, or it's just gas. And then we inject particles at 10 and 100 diameter. And you can see how it affects the spectra. In some cases, it raises the noise at, say, high frequencies or low frequencies. In other cases, it lowers it. And it's very difficult to explain why that is. In fact, I don't know anybody who can explain why that is. It's an open problem, but we can simulate it and predict it. So there's lots of things in the field that we can simulate and predict, but we don't understand physically.
What are they made of, these particles that you're injecting?
They're the exhaust product from the solid booster material, the fuel. So there's a fuel and oxidizer. I'm not a chemist or anything, so we are modeling these particles as radiative bodies that are getting smaller as they propagate, according to models that are given to us from chemists.
I see. So they are getting smaller. Meaning they're disintegrating as they go.
They're they burn.
Okay.
Yeah, so they're going from
So
a,
they're not like destroyed by being shaken around so much.
no, I mean, most of them should react in the combustion chamber if you have a good
I see.
engine. They are ejected. The product is ejected
Yeah.
from a solid booster especially. Yeah, good question. Okay, then you say, well, there's a lot of theories about all this that many people have studied. And I'll just briefly explain this plot. What we have here is half the nozzle contour. So here's the nozzle exit on the left, normalized by the diameter. So this is the center line at 0. And this is the edge of the nozzle or the lip at 0.5. D is the diameter. The X direction here is streamwise direction. So X over D increasing is normalized by the nozzle diameter. So what you're seeing in the right plot, for instance, are contours of the shock waves in the nozzle. And we can predict that with CFD or theory. There's equations where you can predict this. You don't need CFD, computational fluid dynamics. And you can analyze these flow fields and build something like non-dimensional frequency versus X. And you can go in there and you can pinpoint the intensity of a noise as a spatial location in the plume of the nozzle. And by doing that, we can alter nozzle designs and see how it changes the spatial distribution of the noise source. And this is all done with theory and CFD databases. The CFD databases don't give us the noise, but we use theory to understand where the positions of noise are in the flow. And that leads all into instability wave modeling. The majority of the noise from a rocket engine does not come from in the engine. It doesn't come from the combustion. It doesn't come from the pumps. It doesn't come from someone screaming inside who maybe doesn't want to go to space. It comes from everything downstream of the nozzle. All the noise comes from outside the nozzle in the plume of the rocket. These are high-speed slurring, which is just a high-speed camera measuring density gradients with a system of mirrors. There's no smoke. And in these things, from flow left to right, you see there's a high-speed turbulent shear layer. And that grows in these large-scale coherent structures form, and they're called instability waves. They form and grow and burst and break up into sub-instabilities. Nobody fully understands that process. It's the study of hydrodynamic instability in high-speed flow. And as they burst, people believe that creates the majority of the noise. And there's a whole theory behind all this. And I'm going to show some of it to you at least in the first of 3 parts of the technical part of the talk. So get ready. It's going to be mathematical.
So on the previous slide,
Yeah.
is that a next to the left of the circle or the oval on the top plot? Is that a break in the wave there, or is that a
What you're
like a
seeing
dip
here,
rise?
yeah, so this is the center axis of the jet plume. This is where the nozzle exit is.
Okay.
They don't put it on the figure because your light can't go through the surface. Sure, it's solid. And what you're seeing here, everything you see in a Schlieren plot are the density gradients. That's partial rho, partial y. Partial rho, partial y. That's the partial derivative of the density in the crossing direction. So what you're seeing here, this is the high-speed jet shear layer. And it is fully turbulent in the nozzle exit because you have a high Reynolds number. It's fully turbulent also because it's turbulent inside the nozzle, the boundary layer at least. There's a boundary layer of turbulence inside the nozzle on the wall too. So this emerges, the flow goes left to right. Out here, this is nice and like plain looking because the air is just sitting there. It's being entrained by the flow. This is the high speed flow. So where my cursor is now, that's about Mach 0.01. And down here, this is maybe Mach 3. And so I can kind of put my fingers almost together and imagine that's the distance between Mach 3 and Mach 0 at the nozzle exit. So this huge shear layer of energy occurs. And that breaks down into turbulence, and that is where is creating the noise. The breakdown of this turbulence from the high-speed shear layer is breaking down the noise. And that's a huge problem. Nobody's ever really found a great noise reduction concept other than realistically slowing down the flow.
Or removing the air,
I'm sorry?
or removing the air.
Yeah, but I don't know how you would have a propulsion device. Yeah. Some people say, well, why don't we make the bike, like if you're an aircraft, like Concorde, low bypass aircraft, the engines are low bypass, they have small diameters. Like, why are aircraft quieter today, commercial aircraft? Why is a commercial aircraft quieter today than it was in the 1950s? Because of bypasses. A bypass is where your air doesn't go through the core, it goes through the bypass of the engine. Okay, and bypass ratios, that's the mass flow rate of the bypass divided by the core airflow, has gotten bigger. What that means is that the airflow coming out of the engine is slower, but you have the same or even increased thrust. So you see, that's why do we do that? We don't do it for noise. We do it for efficiency. So for those of you who've taken propulsion classes, you'll know that a high bypass ratio turbofan engine is much more efficient than, say, a fighter jet engine, which is more of a turbojet, and much more efficient than a rocket engine, which is not an airbrake engine, right?
I mean, my propulsion classes were back when that was not in fashion
Yeah,
yet.
well, don't worry, there's no quiz yet.
Okay, all right.
No quiz. Anyway, let's just look at
We're just trying to keep you from starting the math part.
oh, yeah, well, the problem is instability theory is a math part, but it's not the hard math part.
All right.
I know, it's horrible. But you invited someone to a seminar who had theoretical in their group name.
I'm just.
That was really a huge mistake. You won't make that again. Anyway, let's just, I'm gonna skip around because, this is a typical flow chart of how we use instability theory to predict noise. So, I'll just tell you what the process is verbally. You have a nozzle, and I give you the nozzle in CAD. And I say, predict the noise from the large scale structures of turbulence, which comes from instabilities. Then you say, okay, well, I gotta predict the instabilities. I gotta predict the instability waves. How do I do that? Well, you have to take the Navier-Stokes equations and perform an instability analysis for basically a shear layer, which is like Mach 3 at one side and Mach 0 on the other. Okay, now that will be the rest of your PhD. That's the beginning. That's it. And people have spent many years doing this. So what they'll do is they'll take the equations of motion and they're going to average them and they're going to add a perturbation. So they say the velocity is an average plus a perturbation, and they'll assess if that perturbation grows or decays. Because if you disturb a flow, like with some disturbance, like if I tap on the table in the lab, that creates an acoustic wave that propagates through the flow, and that could grow and become an instability wave. And without looking at this too much, I want to just tell a story about people studying rocket noise and jet noise. There's a professor at University of Texas in Dallas, and that's a lab. It's an anechoic chamber, meaning it's low noise inside. And there's a jet nozzle, small, and there's a jet flow. And these jets have modes, just like in dynamics, you might learn about modes. And it's very hard to know what mode the jet's in without doing some measurements. And so they were studying this jet in a particular mode. And they had trouble keeping it in that mode. It's like an unstable mode. So they're forcing it to keep it there. Now, one of the grad students at the other side of the building would come in and out at a certain time of day from lunch. And they just discovered that this grad student, who's closing and opening the door on the other side of the building, this is like 100 yards away, was sending like some kind of wave through the building that kept pushing it out of the mode. And it was just from that one door. When they discovered this, they go into the other door and it didn't do anything. So you see, these things are ultra sensitive.
How did they even discover this?
I don't know. It's an amazing thing that the one thing they could consistently do is open and close that door and somehow always disturb the mode. But somehow like an acoustic wave or vibration through the whole building came up and it just perturbed the little nozzle a tiny bit. And then the whole thing went to a different mode. So you see the tiniest of perturbations change the flow. So how can we study a flow that's turbulent for a really important problem in a laboratory environment that's highly controlled? It's highly chaotic. The smallest of perturbations can interrupt the flow. This is a typical chart where you take the jet flow in geometry, you predict the instability waves, and you predict the outgoing acoustic waves. And there's lots of papers on this, and if you're interested, you can email me and we can look at them. This is just a big picture of the approach. You have the equations of motion, and you perturb them, and you can write down a solution for the pressure, that's P, outside the jet flow. And it goes as this horrible equations that we have to solve using the method of mesh asymptotic expansions. And then we can predict the noise. So, and then there's time. I'll show you some calculations. So this is your typical jet. This is the nozzle, flow goes left to right, and it's breaking down in turbulence, and Mach wave radiation and shock noise going upstream. So we're looking for more of this downstream radiation. These are predictions of the mean flow, the average flow field. And this is what the instability analysis looks like. So basically the y-axis here is your amplification of waves at non-dimensional frequencies. Now, it turns out the peak frequency of all jets, it doesn't matter if it's a volcano, a rocket engine, an aircraft engine, or a little compressed air can, peak frequencies around a Strehl number of 0.2 to 0.3 in the downstream direction, the direction of the flow. And that's also the most unstable modes. And we can assess this on a per mode basis. These are modes, azimuthal modes, 1, 2, and 0, 1, and 2, for instance. And you can see it turns out the mode for this particular nozzle and jet is most unstable around 0.2 Strehl number. So Strehl number, you know, is a non-dimensional number like Reynolds number, non-dimensional frequency.
So this is not. So this is how you call the number?
Strehl number, yeah. So Strehl number is non-dimensional frequency.
Yeah. I just-
Yeah, non-dimensional
I used
frequency.
to Stokes numbers for STD.
Mhm. Yeah, Stokes flow is another, also be assessed that way. If you have like Stokes second and third flows or shaking flows.
So just real quick, so this number indicates a position in the flow? Or not?
All this is telling you is what the modes are on a per frequency basis and how unstable they are.
Okay.
And from that analysis, we can predict the outgoing intensity. So here's examples of proper orthogonal decomposition of the modes of turbulence in the jet flow. Does anybody know proper orthogonal decomposition? No, nobody? Wow, that's just a general statistical framework. Okay, you guys yeah, hit up the math classes. You got a great math project there. It's a way to take any signal, a random scientific signal, and decompose it in its most energetic modes. So if you take the sum of these energetic waveforms or modes, you get the original signal. So if you have a sine wave, you would have one mode and it'd be the sine. If you have two sine waves and you add them together, and you multiply the second sine wave by say 10%, the most energetic sine wave will be the first one. This will be 1 times sine of 2 pi ft plus say 0.1 of sine 2 pi ft with twice the frequency. And it'll turn out that the by doing POD, you'll have two modes and you'll be able to exactly recover those sine waves. Now imagine you have a random signal, which you measure from outer space. You could do POD on the signal to find out the most energetic modes and know their frequencies and statistics. So POD and dynamic mode decomposition, which is a little more advanced now, are the statistical ways to analyze signals from scientific data. It is very powerful. So it's an awesome tool to learn. And these are POD analysis where they show energy on a mode basis. And those are contour plots. I'll skip that. So let's look at CFD. I got maybe 15 minutes where you get the hook. You know, like the vaudeville acts.
So I thought you were trying to
Yeah, let's look
not use CFD.
sometimes we use CFD and sometimes not, just depends on the problem. Sometimes we combine CFD with theory. Yeah.
Okay.
Yeah, so if we use CFD and it's unsteady, then we can use a POD
Mhm.
analysis. In this case, we use CFD to get the average flow and then do the instability analysis of the flow field and then extract the unsteady modes. We can also do that directly from CFD and compare the two, and they better be the same, or else we're wrong.
Okay, so CFD for sure is gonna be working out properly.
It depends, like CFD is a tool and it's not always right.
Okay.
It can be very expensive, right? So NASA AIM supercomputing can be like 60 to 70% aeronautics, which means it's on the CFD side. So the problem with CFD is you get large numerical databases and you have to understand them. So I just give you a large numerical database. How do you understand that? You have to use statistical tools like POD. That's one of many. And you just do basic statistics. You find averages of your data. That's fine. But with a large numerical database, how can you understand the physics?
Mhm.
Here's one. A rocket noise, jet noise in general, generally scales as the velocity to the 8th power. The 8th power. How many 8th power laws do you know in your life? It's very high. It's one of the few. So the noise scales as the velocity to the 8th power. That was found in 1952 by someone who was about 22 years old. And he was knighted for that. Sir James Lighthouse. Lighthill, excuse me. And he didn't have CFD. Now, if we take our full supercomputing simulations today and analyze those databases and measure the total acoustic radiation, it goes as U to the 8th. So if I do a CFD simulation and it doesn't agree with that theory, I'm probably wrong. So this is the power of theory, that so many people are working on numerics, machine learning, large databases, and you can't tell me the physics. Because it's all governed by the Navier-Stokes equations. If I take the Navier-Stokes equations and don't solve them numerically, I analyze them.
I'm not arguing with you, but it's better or not.
I'm starting to be, I'm telling the students this, I guess.
Yes, I guess.
Because so many people do purely numerics. And you will never understand the equations of motion or physics unless you study PD. So see, I'm a professor and this is my job to be critical of the community.
I'm on board.
Yeah. Let's look at the CFD itself. This might be called colorful fluid dynamics if you want to joke with the CFD people. It's really computational. And we do something called spectral large eddy simulation. Large eddy simulation is an unstudied CFD technique where you only resolve the largest scales of turbulence. Why do you do that? Because the largest scales of turbulence contain most of the energy. And you filter away and model the small scales of turbulence. So this is one of the emerging and most popular ways of doing things. It's spectral because it has spectral numerical accuracy, which you can traditionally only have from Fourier or spectral methods. So let's look at some examples. This is your nozzle CAD. That one's from NASA Glenn Research Center. On the right is your computational domain. It's about 30 diameters in the cross-stream and 66 diameters downstream from the nozzle exit. And this is a grid. It's fully unstructured. We put many layers of the boundary near the nozzle exit here in the flow of the left to right. And we basically build up huge unsteady databases of the flow and to analyze them and predict the motion. So for example, if we wanted to point this at some lunar surface and build in the particles, we could do that. Let's just try and, there's some pictures of that flow. So this is basically a slice of the jet. If I go a little bit downstream or just downstream the nozzle exit and I take a plane and make a contour plot, you're going to see X momentum. So this is the center of your rocket nozzle, for example, and this is near the nozzle lip or the edge of the nozzle lip. And there's momentum. This is a slice of the nozzle itself. So you see there's turbulent boundary layer, you have shock waves in the nozzle, and a little mock disk or barrel shock forms at the nozzle exit. And then you have your exhaust. So this is all fully simulated. One simulation using spectral LES, which is the cat's meow, takes 2,000 processors. That's not cores, processors, 30 days, continual runtime. Some of the largest CFD or computer calculations today have been run out of Minnesota and Stanford, and they just eat up the processing power, just eat it up. Kind of like astrophysics class. Here's another example. This is your LES, this is your nozzle, flow left to right, and this is the center line on my cursor. So this is the center of the nozzle, this is the nozzle exit. It's the same flow, and you're seeing a numerical flaring on the top. So that's the LES. On the bottom is your experiment. And that's a picture called the Schlieren image. It's slang for streak. And hopefully these lines match up because that's like the shock cell structure you see in your exhaust. Okay. So we do both like visual, qualitative and quantitative comparisons. These are just some more pictures of what you got. This is actually noise predictions versus experiment. X-axis is Stroll number, Y-axis is sound pressure per unit Struhel number in dB. And let's just look at one. The black line is the experiment, and the red line is the prediction. And so these were produced a few years ago, and it's hard to make better predictions than that. The problem is you can see there's error. Like, for example, there's some of these tones up here. This is fall off, that's due to digital signal processing. Don't worry about that. But everything else should be compared to 1-to-1. And you'll see in some cases we're more than a few dB off. But I just told you, if I turn off one of my engines on an F-18, I only have a 3 dB change. So really a microphone accuracy, if I have a microphone, these are really expensive scientific microphones that be about $3,000 per microphone. And they will have plus or minus a half a dB accuracy. So you can see the predictions can improve. They're wrong because I'm outside the uncertainty on my measurement, which is really bad. So for those of you in that field, it's a great thing to work on. And in the interest of time, this is a POD on, this is just the math, basic POD, which they teaching turbulence classes usually know, of how we extract the POD like we did in instability waves. So I'm going to skip that. Okay, got 5 minutes maybe for me to entertain you with the idea of cross-spectral theory. So this is where we want to take a database of like LES or instability wave predictions and predict the unsteady pressure on the rocket or the launch pad. Okay. Now, this is the problem statement that I faced when I was in NASA. They said, okay, we have all this CFD. We have all these numerical databases. How do we predict the unsteady loading on the rocket itself or bystanders or the launch pad? Is there damage during launch? How do we predict the structural dynamics? And to do that, we need to know the pressures everywhere on the vehicle, but we don't really care about the pressures in the time domain. We care about them in the frequency domain, which is a Fourier transform. Now, usually in our lives, we say, measure the temperature at a point on the table, measure the pressure up there on the ceiling, measure the velocity over that point. But we want to have one equation where we can predict the pressure at 2 points simultaneously in a relation between each other. So I always feel like this is a big disservice in my own education in the United States, that we always focus on like prediction at a point. And you got to start thinking like, if I can predict things at 2 points simultaneously, then I can relate 2 points to 3 points and also predict everything everywhere simultaneously in one equation. I mean, so imagine you're a new NASA researcher and they say in the civil service at say Langley, and they say, here's all your databases, predict this. That's your job. Go away. They'll come back to you. That's the attitude I have, the very aggressive attitude about research. So you can kind of think about that. Here's a mathematical overview of how you do it. And this is kind of written for experts in the field. So, I've been doing this for a while, so I'll explain the big picture.
Was that your experience at NASA?
My experience with NASA was you can do anything you want as long as your Model T is black. Henry Ford told the assembly line workers that or people buying original Fords, that you can have any color you want as long as it's black. So the new NASA researchers at the time, they said you can do whatever you want as long as it's in your field. So they were like, don't go off and do structures, you are in acoustics, or don't go off and do this or that. So they gave you a lot of research freedom and to work on really, really hard problems. Even if you can identify the problem, that's even better. You say, this is the problem I think that's important. And this is the impact it'll have if I can solve it. And this is my plan to solve it. And if you can tell the story of identifying a difficult problem and how it'll help them, then you'll go a long way as an independent researcher. So in NASA. In this case, we'll take the Navier-Stokes equations and we're going to try and solve them for the pressure, the acoustic pressure outside the jet. And that whole approach goes through a theory called acoustic analogy. And you can write the pressure equals an integral of everything in the Navier-Stokes equations in the jet flow. And then you take the cross-spectral power density of the pressure and you're done. That's how easy it is. So let's look at the equations. There's your coordinate system. So there's your nozzle. And we have X1 and 2. And this is say where you have one microphone and another microphone and you have pressure. And there's some system of coordinates that relate the distance between turbulent structures in the jet. And so our solution will be as a function of two spatial positions. For example, I'm saying temperature at X1, pressure at X2. Now I want pressure at X1, X2. And they're defined by a vector between them. That's very confusing to think about. I made this figure and I stared at it for a month and I think I understand it now. If you see something that I'm missing, please let me know because it can be very confusing. So here's an Analytical Journal article called Cross-Spectral Acoustic Theory. This is G. This is like a spectrum, but instead of at one point, you have two. And it's a function of frequency. So you see the previous plots I showed you? That's taking pressure and basically find the power spectral density, which is like a Fourier transform, to put it as pressure versus frequency. Here, this is pressure versus frequency, but it's also a function internally of two spatial points in that one. Why do you need this? Because this is what goes in, G. That's the cross-spectral power density that goes into the structural dynamicists that predict the response in the rocket body. Okay. Wow. Everything on the right-hand side, I'll just describe. This is two volume intervals in the time interval. So we take our CFD simulation and we calculate everything in here, which is a function of densities, velocities, pressures, and temperature of the turbulence in the plume. And we get this number. What do these terms look like? They look like that. And that's derived completely analytically with no assumptions from the Navier-Stokes equations.
Just typing it.
Well, yeah, it did take a long time to type that, but it took longer to write it. Thankfully, now people are more into Mathematica, and I didn't learn that until later. So we have lots of great computer systems now to do this that would save you time today. But the good thing is you can copy and paste that once you type it into Fortran or C, because they won't accept other languages because they got to run on supercomputers. That's a whole nother discussion. And basically everything in here is just Mach numbers and vectors between sources and those kinds of things. And then you say, okay, you did all this work. Now you got to validate it. They say, prove to me your theory works. Well, that was easy because about 7 or 8 years before I did this, they developed an experimental database for someone to validate a theory like this. And Tim Colonius at Caltech went to NASA Glenn Research Center and he went into this facility. So if you go to NASA Glenn or the airport in Cleveland, anybody been to Cleveland before? It's cold. And you look out the window of your aircraft, you're going to see a giant dome. The dome is about 80 feet radius. This is what's inside the dome. You can see on the walls, those are anechoic tiles. It's beautiful. You're in there and you look 80 feet in any direction, there's this anechoic chamber.
They build it just for that?
Yep.
Wow.
Well, not for this experiment, they've had it a long time, but it's used for these types of experiments.
I see.
Yeah. There's the nozzle. That's about 2-inch diameters
Who's managing
right
it?
there. Oh, I don't know who manages that. That's a good question. I don't know.
So-
I don't know. I only know the researchers, right? I don't. The managers seem to have a lot of turnover.
Mhm.
Now there's put this giant metal thing around the plume. And on this metal thing, there's little rods. And at the tip of each rod is about a $3,000 microphone. So 3,000 times 80. Well, we do the math. I only do math. I'm getting paid by a grant. It's another joke. Okay. No jokes in here. That probably means you got to start wrapping up your presentation. They take this database, and what they do is they take the data from every microphone, which is measuring the noise at 200 kilohertz, and find the cross spectrum. So if I take that equation and I compare it to the cross spectra, which is basically for each microphone pair, for every 80 microphones, it's got to agree. Okay.
And these don't mind if they're getting shot at by hot gases and.
The microphones won't be in the turbulence.
I see.
Because if you put a microphone in the turbulence, it will break. And then you pay $3,000 to replace it, basically.
Yes. Okay,
Yeah, which is bad.
so they're.
So, yeah, they all have a lot of interns at NASA and they let them set up microphones. It's normal to have microphones break. It's just built into the budgets. So that's one of the great things about being experimentalist. Anyway, this is a plot I made for one jet condition from that facility. The y-axis is sound pressure level in dB. The x-axis is that non-dimensional frequency. The blue and red lines are predictions and the black lines are experiments. So for using something that had no CFD, where we approximated the turbulence statistics analytically, it agrees really well. And we do this over Mach numbers from 0.5 to 2 and temperature ratios from 1 to 4. And that's coherence, which is a whole nother validation. There's a better view. Now we've moved the microphones up to the edge of the turbulent flow. So these microphones, if there's this high-speed turbulence and one little turbulent eddy goes up and hits the microphone and breaks, then you're gonna pay $3,000. So you make sure that microphone is close to the turbulence as possible, but outside of it. Because nobody wants to pay that much money all the time. So these microphones, you're like looking down. See, there's the 2-inch diameter nozzle. This is 80 feet away, that wall. And then you see each one of these things, that little tip is lined up. And even the way they arrange these microphones is optimized. There's actually computer codes that optimize microphone placement. is you can use the data from the microphones to reconstruct the turbulent field. That's another reason it's done. And there's some predictions and experiments. You
So
can
you
see-
got a grant, sorry, I'm sorry.
Oh, no, go ahead.
You got a grant to go test this at this facility.
These experiments were done before I got involved.
Uh,
So there was a professor at Caltech who worked with NASA Glenn to do the experiments. I came in later as an employee and now as a professor to look at it.
okay,
Yeah, so I don't do these experiments. They're done by the team at NASA Glenn. I mean, this is a huge facility.
yeah.
They have a lot of funds going through it and people, so it's.
Mhm.
You really need to be an expert experimentalist to do this, which I'm not.
No, right, but you're like, oh, I made these new calculations. I think it would be great to test them in this facility. And then they sort of reward you time there. Is that,
Oh, if you're an experimentalist,
no,
there's,
pure you, like, in order
Yeah.
to do these plots, you have to have them run.
the database was produced before I even knew about the
I
problem.
see.
So you
Okay.
see these guys are
They
a
made
lot
all
older
these
than me.
measurements, and you
Um,
just fit them as a theory. So it's sort of-
Well, they had an experimental database, which they gave me.
Okay.
And then I took it and I made predictions into
Okay.
comparison. They also keep some of the database to themselves, so they can verify that I'm honest. So there's some blind predictions. But it's why should you trust a professor? To be honest, if you're in the government,
Mhm.
it's a great question, because there's lots of people, lots of pressure. And people today, unfortunately, falsify their data.
Mhm.
And so what they're gonna do is give me part of the database. And I say, you keep that other part of the database yourself. So you have some cases where I don't have. And I'll email you the predictions and you compare the predictions to experiment. And they better match. So that's a blind prediction. So really good programs, good program managers, I think, believe in blind predictions. Because it's like, you give the prediction, it better happen. It's like Einstein made blind predictions. Think about his work with relativity. He didn't have a lot of experiments to look at. So it's truly like a true theoretician making predictions which are still being validated today with large scale experiments. That's amazing. And they do that in this field too. Anyway, that's really wrapping it up. The major conclusions is rocket noise is really loud. That leads to rocket failure. And sometimes destruction. It can lose payloads, thermoacoustic instability, burst rocket engines too. They're difficult for communities. You hear that, like there's some communities in Texas involved with SpaceX, they're complaining about the noise from rockets. Arizona Spaceport complains about noise and potential noise. So we want to reduce noise, but nobody's really designing rocket engines to be quiet. So at least we can measure the noise and understand it. And from my point of view, I do modeling really. We want to understand the physics of the turbulence and the noise from the turbulence in the field of aeroacoustics. In the rockets, all the noise is coming in the exhaust. When you see a rocket launch, and I'm sure you can hear, and you go out to the East Coast, you can hear it. It's beautiful, it's powerful, it's low frequency, you can feel it. It's an amazing thing. Just think all that energy is coming from the rocket exhaust. In fact, one way to look at it is when you fly on a Boeing 747 and you take off and you get to altitude, you fly at cruise. That has usually 4 engines on the original 747. So that's a lot of energy it took to power those engines. Now, if I took the acoustic power from Mach 0 to cruise, it would boil 1 egg. So what does that mean? It means the total energy from the engine is so small acoustically, it's all being dissipated in the heat. Anyway, it's an ongoing challenge, and I'm really thankful for you having me here today. I'll be here as long as you want for questions or listen to your research. It's awesome, and so thank you so much. Yeah.
Thanks. So, I don't know. I
Okay,
don't have my jacket,
thank
but-
you. So, oh, sorry, I didn't see that.
Sure, I think on slide 40, you showed, I think that was the first slide where you compared predictions with, yeah, exactly.
Yeah, these are LES, yeah, CFD. This is pure CFD using
But the experiment is actually measured, right?
the experiments are, what they do is they take a microphone and they measure the pressure at
Right.
200 kilohertz, 200,000 hertz. Then we find the power spectral density. which is the Fourier transform times its complex conjugate. In not discrete. This is discrete data, I do more, but if it was a continual waveform.
Right.
So that's what you're seeing, the black line. So the y-axis is sound pressure level, the x-axis is non-emission frequency. Yeah.
Okay, thank you. I think I got that. What I don't get is why, and I'm mostly looking at the plot on the top right because it's most visible to me, but
Sure.
why is there so much more, well, noise in the red curve than the black curve? Is there some physical phenomenon averaging things out, or?
Yeah, I mean, these are just average predictions. I'm not cherry picking. I'm not showing you our best predictions. I'm not showing you worse. This is just one data set.
Oh, what do you think?
And you're right, it's wrong. It's wrong.
What do you
The
mean?
predictions are wrong. Right? Because they don't match the experiment. They're not within experimental uncertainty.
Huh,
I
okay.
thought you said 3 dB is not so much.
3 dB is a whole engine. If you're on an F-18 or any other aircraft with 2 engines, what if you have a rocket with 2 engines? I shut down one engine, the overall sound pressure level goes down by 3 dB. So 3 dB is a ton of noise, but the microphones are only accurate to plus or minus 1/2 dB. Does that make sense? So then you say, well, you know, your group sucks because your predictions are wrong. But let me tell you, people have spent many PhDs designing just CFD codes to do these predictions.
Yeah, I'm not saying anything like that.
I mean, I would say that. You know, I have a lot of friends who did their whole PhD on CFD for jets.
Yeah.
I did my whole PhD on shock wave shear interaction with turbulence and noise. And you know, that's a theory. It's not really a CFD based thing. And it just brings more questions and answers like all fields. Like I think all good research just like brings out more questions and answers, you know, that can be really awesome. Actually, if you have a good research project, you're like, oh, my research didn't work. I'm not successful, but then you have all these new questions. I think that's just exciting. That's a successful program to me. But yeah, so people still, especially in Europe and Asia, because Europeans and like Japan, for example, has very strict requirements, and they pump a lot more money into noise in the United States.
Okay, I have one question from the online participant, Andy Torres. So he says, I see that at KSC, they flood the launch pad with water to deafen the sound. Have you modeled that before? Any comments on what is happening there?
Yeah, so there around the world, people discovered, it's a great question, that if you have water injection into the flow, it can reduce some noise, certain types of noise. In fact, it reduces the noise that's due to shock waves turbulence interaction. It does not reduce the noise from the large scale turbulence structures. In fact, before my time at the Jet Physics Lab in NASA, not JPL, I'm talking about the Jet Physics Lab, which is in Langley. They took model engines where they put in a combustion chamber, it's hydrogen-based combustion, I believe. And they had some model nozzles and they did water injection and they did scientific experiments. So I think they're the original ones. And they showed that certain noise sources are reduced and other ones are not harmed. Then you might say, well, what's the physical mechanism? And that's really hard to answer, but there's a clue. The clue is that certain types of noise are disrupted by water droplets. And that's because you're breaking up the coherence between the shock cell structure, which you see in the plume, and the turbulent shear layer. But you're not really breaking up the large scale structures themselves, and they continue to radiate noise. Does it reduce noise? Yes. Is it as effective as people think it is? No. The water is also good. It does reduce noise and reduce sonic fatigue, but it also reduces the plume impact on the launch pad, which is a, you know, more of an aerodynamic too. And also, if there's a bed of water under your rocket from the rainbird system, that's good too, because the sound waves mostly go in the direction of the nozzle flow. And they go down and they hit the launch pad and bounce up. Now, if I have water on my launch pad, that's good because these high intensity waves, 180 dB, are going down and they're hitting the water and bouncing up. What happens when a wave hits the water? Well, some of it's going to reflect and some of it's going to go in the water. So the entire energy of the wave is not reflected. Like in this room, I'm talking, which might annoy you. And the sound of, nobody laughs. Sound of my voice hits the wall and bounces back, right? This is a hard wall. If I make that wall out of sponge, then some of the wave will be absorbed. So the water acts as like a way to absorb the waves. It's also interesting if you think about, say, submarines. And there's a helicopter above the water looking for your submarine. The noise from the helicopter comes down and hits the surface of the ocean. Some of those waves from the helicopter bounce up in the atmosphere, and some of the waves go into the water. And of course, good submarines are going to have good sonars and know there's a helicopter above them.
So, it's a wave, so I can't help but think about, how they would use, for a specific frequency, you can use interference to cancel out, a wave. So is that something that was thought of?
Oh, yeah, I mean, that's probably, it's probably one of the most, thought about like ways to reduce noise is like active control or cancellation. Right, because if I have two waves and they're out of phase and they have the same properties, then you hear nothing. The problem is the source is turbulence and it's distributed.
Mhm.
So my noise is all frequencies, it's broadband, it's many different amplitudes, and it's distributed spatially. Now, it's a general principle that you cannot cancel out incoherent noise. The problem is there's incoherence between the sources, so it's impossible to do noise cancellation for a rocket flow.
So you couldn't, when you're doing your analysis, you couldn't identify specific frequencies that have high, the ones that would have the highest amplitude to them and then target these.
So that's right, that's why we do instability wave theory. So instability wave theory will tell us the most unstable mode, its amplitude.
Mhm.
If we can find a way to destroy that instability wave or stop it from happening or reduce its strength, you will reduce the noise. And that's where active noise control comes in. People have put in plasma actuators and nozzles and actuate them with active flow control to change the turbulence structure. You're not doing within the noise directly. You're trying to control the turbulence.
Yeah.
People also do this for all kinds of other applications.
I was thinking, you're outside and you're basically generating another 180 dB.
Yeah. But then
You
if,
know.
if you did it perfectly, it would still only cancel out the noise at discrete locations,
Mhm.
not all locations. So.
But if you could pick these discrete locations to be the most amplitude ones,
Yeah.
is that something one, I don't know.
I would say it's.
Yeah.
It's impossible.
Okay.
Yeah, which I rarely say something impossible. I think it's impossible. All right. Question.
At the end of the presentation, you briefly mentioned, like the acoustic energy that, so took from takeoff to cruise.
Yeah.
Right? And then you said it equated about to like 1 day, right?
Yeah. and
So
on your
has
kitchen.
has anyone ever quantified as in like measured or predicted the amount of acoustic energy that a rocket engine has, like a?
Yeah, I mean, you just do the same scaling analysis. So the power, you can calculate the power if you got pressure. And you can look at it on a sound pressure level basis. And it's going to be about the same fraction for a high-speed jet engine. The flows are self-similar. If I take the flow field that I showed from like a Schlieren of a jet engine or a 2-inch nozzle or the little 1 millimeter diameter air canister, they're all going to have self-similar flows as long as the Reynolds number is high. Doesn't matter if you're a volcano or a little air can that has a millimeter diameter nozzle. They're all, as long as they're high Reynolds number, they're all going to generally radiate the same percentage of overall noise versus total power. And so the 747 example is the classic one of, for rocket. There's also rockets all kinds of different sizes. But if I look at the spectra from a rocket engine versus a little air can that has a diameter of say 1 millimeter, I can overlay the spectra. And they'll look exactly the same if I normalize it. Just like you normalize flow with Reynolds number. Remember Reynolds number?
Yeah.
Like you can normalize flows, it's all similar theory. You can do that for noise from rockets or jet engines or 1-inch nozzle. I mean, that's why we can do a lab experiment of a 1-inch nozzle and scale those results to full scale.
So what you're saying is, like there's like about a fixed relationship between, like the power and the acoustic power.
Yeah,
And it doesn't matter the scaling, right? But is there a difference in like this, or the difference lays in what frequencies? Like,
yeah. So a larger engine will have lower frequency noise because it's bigger. that simple. Right, so if the peak frequency is Stirling number of 0.2, for the noise from the large scale turbulent structures, it doesn't matter. Stirling number goes as what? A frequency, a diameter, and a velocity. So if you match Stirling numbers between the two cases, they'll both have a peak of 0.2. It's just that you have a different diameter. Right. The diameter gets bigger, then the Stirling number will change.
So Mike Kinzel is saying, yes, saying, be sure to. We should give you a hard time if your acoustic predictions neglect multi-phase related attenuation.
Yeah, that's true. We don't take into attenuation from particulates in the atmosphere or something.
Okay.
I guess that's something he's volunteering to try. That's how I interpret it. So, but thanks for the comment. It's a great comment.
You mentioned that the acoustic waves from the rocket launch come out of the way of the nozzle. Why not use patterns on the launch pad to break those waves?
Patterns like on the launch pad surface?
Yes.
I guess that's why they put water down. They have water on the launch pad surface to stop the reflection. I mean, the noise is coming from a volumetric source. Right, so if you have your rocket engine and your rocket engine has an exit diameter, your noise is coming from like at least 35 to 40 diameters from the nozzle exit to 40 diameters downstream. So if my rocket engine is just at the top of the pad, it's taking off. I have about 40 diameters between the engine and the ground. What do I do to the ground to stop the noise coming out of that turbulent flow? It's a question for you. Like, what can I do to the ground to stop the noise coming out of the turbulence? The turbulence is in the air. It's behind the engine, right? Does that make sense? Yeah, you can do something to the ground to try and stop the reflection, but the acoustic waves and even the exhaust from the engine are propagating down and hitting the ground and then going in different directions. So they do things to the ground. They have a trench so that your flame doesn't burn up the launch pad or something. Yeah, I think that makes sense. It's really hard to grasp. People in the 1940s thought all the noise from jet engines when you were coming into being came from inside the engine. It was shocking to people when, we were showing with experiments that all the noise was actually coming from, 10 to 15 diameters downstream from the engine, in early engines. It's out there in space. It's crazy. It's totally non-intuitive, I think. Yeah.
Okay, we have a follow-up from Andy Torres again. So how could you reduce the large structure noise? Or the turbulent, okay, let me read the whole thing.
Yeah.
Could you imagine or comment on the possible system to reduce noise from the large turbulent structure or challenges invoiced in designing such a system? Is it a terrible idea to try design a huge flow straightener?
Well, I think there's been, I guess it's a really great question. The thing is, I can think lots of ways to actually reduce the noise, but they hurt performance. The goal is to reduce noise without hurting performance. I don't want to add weight. I don't want to reduce specific thrust. If you go to Boeing, you go to GE, you go to Airbus, you go to a rocket company, and you say, I can reduce your noise. They say, great. By how much? You say, by 3 dB. They're like, you are a genius. What is your concept? It's like, it is this concept. And they're like, well, that draws, we are going to lose 0.1% thrust. Your idea is rejected, period. Let me tell you how hard it is to get a noise reduction concept on an aircraft engine or something. Let's say you do come up with this amazing noise reduction concept, and you go to the Navy, you go to GE aircraft engines, and they say, this is great, but it's going to extend the length of the engine by 1 inch. And then I say, so what? I've solved your problem, or I came up with an idea. The US Navy will say that it no longer fits on the box that goes on the aircraft carrier. That is a true story. So even if you forget about all the other problems people have in terms of like engineering, because it is a systems problem, you still have to think of a way to maintain or increase performance while reducing noise. And that is just really, really hard, really hard. And that's like the holy grail, if you will, the field in the jet and rocket noise that field. So, but I mean, this has been around for a long time since, really jet engines came into being, is, understanding jet noise reduction. And like I said in the talk, the major reason that noise from commercial aircraft have gone down is because the engines got bigger. And if you have a bigger engine, you can have the same thrust and reduce noise. But it's not done for noise, it was done for efficiency. So when you go and see these huge aircraft engines, you know that they're quieter, but only because they have a really, really big fan. So you got the more airflow going slower. You're going slower because the noise goes as the velocity of the power. So the velocity coming out of the engine has gone down, it scales as u to the eighth, and the noise has gone down. But it was never really done for noise, it was always done for efficiency. Because that's connected to money. Sorry, but it's a good lesson,
The ways of the world.
yeah. Okay.
Okay, I think this is
Yeah,
a
we'll
good
talk.
stop. Oh,
I just had, or,
let's do the last one.
okay.
Okay, you did the last.
I just had a question about launching out of like a solid structure, like a silo or something.
Oh, yeah, like that.
If that prevents noise from people like hearing it, but does that add structural fatigue because it's reflecting?
Yeah, I mean, it's
noise
such
from
an
all
awesome question, because people have thought a lot about this. And because we do launch things out of tubes. And there's lots of examples, like land-based ballistic missile, silos on submarines. And so these are basically in tubes, which are metal, and they act as a resonator. So the frequencies, which go as diameter, multiply diameters of those tubes, are amplified. And so people think a lot about how is my missile going to come out of the launch silo or submarine. And so that increases noise a lot because it's resonating.
Not.
So that would be bad. So if you look at a submarine launch, for example, which is a wonderful way to like think about how they overcame the problem, is sometimes they're gonna like have these large missiles in the tube, and they're gonna like use like compressed air, if you will, and they'll like push it out of the water, and then the engine ignites. So they have engine ignition once it's actually above the water, and then they avoid this issue.
Okay.
Yeah, so that's you can actually see these videos online. But that doesn't talk about the land-based launch systems, which are ignited. So if you look at satellite photos of the People's Republic of China, they're working very hard to build more land-based missile silos. And they're all over the country. And so I think they're probably new leaders in the field of how to do this. And
So they figured out how to do this.
well, I mean, it's always been done, but it's a hard problem to solve because you have this very intense noise and want your missile system come out of the silo without exploding. Well, I wouldn't mind if there's exploded, but
Very
that's just
interesting.
me, But great closing question. Thank you again. I'll be here a bit more if you want to talk.
All right.